My name is Prasanna Swaminathan, and I am with Media Math, and I will be talking today about server-free architectures. But first, a little bit about us. Can I get a show of hands? Who all is familiar with ad tech? And who all is familiar with RTB? Okay, not many of you, and that's expected. So think about when you go to a web page, let's say New York Times or let's say YouTube, and you see a banner ad on the page, or in the case of YouTube, a video ad that precedes a video. So these ads get populated by ad exchanges. Essentially, the site will set up an auction. MediaMath plugs into those exchanges on behalf of advertisers and will make bids based on how valuable we think it's worth. So the advertisers will come to us with their creatives, essentially their ads, and we will run them on their behalf. And so we do this, we'll submit these bids on these exchanges in real time within about 40 milliseconds, millions of times per second. So that's a lot of information going on. That's a lot of tech there, a lot of data there to take. And so correspondingly, there's a lot of technology behind it. So to help us deal with this, we have a very experimental culture. Anyone, any team can play around with new technologies, new platforms, and if it solves the right problem in the right way, get it into production. All right, but this talk is about web app architecture, where we've been, where we came from, where we want to go, and how to use some of AWS's services to get us there. So what is server-free architecture? We're not talking about apps without servers at all. What we're talking about is apps without managed servers. There are apps where you aren't actually provisioning servers, you aren't actually cognizant of what servers are running your code, how many servers, what are their configurations, things like that. That's sort of what we're talking about here. All right, so let's start off with where we came from. So why should I care about this? Let's go back to the 90s. Back when web hosting was first becoming a thing, going back to shared hosting and sort of as a semi-next step VPSs, where you'd pay for share of virtualized server time, or just for the virtualized server in the case of VPSs. You could manage these by control panel or by FTP or by SSH. And so this is something that's fairly basic, fairly low maintenance thing that you can get set up and running. In the case of VPS, this is also how people would scale up bigger apps by using VPSs and other kind of hardware. But servers are difficult, right? Which is why shared hosting was a popular concept, which is why cPanel was everywhere, right? You have to manage parity between servers. You have to manage dependencies between servers. And you have to provision and deploy everything that you're trying to do. So we know this is a problem. We know this is tough. There are entire disciplines and teams around DevOps and around making this easier to swallow. We also have tons of products, Ansible, Chef, Puppet, Capistrano, insert cool name here, that are used to provision and deploy these servers, right? So it's a tough problem, and it's something that's not really going away. In addition, as our web apps get complex, the ways that we scale change as well. So if you think of a simple web app and that gets more and more traffic, you have to scale that in terms of operational volume, right? You might scale that vertically by getting bigger, beefier servers, faster databases, things like that. But you also have this operational complexity that you have to deal with as well as you get past a certain point. Right? We now have, we don't just have one server that runs everything. We don't even just have, one web server that's web-facing and a database server that it talks to. We now have load balancers and clusters of web servers and clusters, sharded, replicated database sets and caching servers and things like that. So we move from single server to server per concern to clusters. So to try and help us deal with this, platforms like Heroku have sprung up, Heroku being the most popular, the most common, where you pay for your use of resources. right? So typically managed over VCS, Git push Heroku master. I'm sure everyone's familiar with that. But you're provisioning by expected usage, generally based on tiers. And so the trade-off here is that for sacrificing a bit of control and sacrificing a bit of knowing every little bit, you get some convenience, you get some abstraction, right? Which is really the key component of this. What we want to do is we want to remove as many barriers as we can to get our code up and running, right? Really, in an ideal state, if you're willing to sacrifice the control and you just want to get your app up and running, you don't even need to think about the execution environment, right? There's just code that runs, and it just runs, in space, in the ether. And Heroku doesn't actually solve the problem. It gets close. It simplifies one dimension of scaling. We can just sort of choose services, and they'll connect the dots, and we can pay for tiers, and they'll handle what that means in terms of servers. But you still have this concern of operational volume, right? If you are paying by your expected usage, you still have to consider how much overhead do I want to pay for, right? How much is worth it to me, and we'll make sure that from what I expect, nothing will go down, nothing will get set on fire. But additionally, static hosting on Heroku requires a runtime, and most of the platforms, as far as I'm aware as well, they require runtime. Heroku's actual recommendation is to serve a static site through a rack server or through a Node.js server. This is kind of like asking Elon Musk to deliver coffee to your office, except it's worse because it turns out that Elon Musk is pretty good at inventing the future. And so when we ask him to get coffee, he's slow and he gets some of the orders wrong. So this isn't a great setup. This isn't a great state. So what is our ideal state? We have a static site. We want that to be delivered by a CDN, fairly basic there. They're set up to handle that. They're good at that. We have a server-side process. We want that to be standardized. We want the runtime to be consistent. We want them to be isolated, so that we can sort of have these talk to each other across some boundary, but not sort of have one need to reach into the other. And we want to abstract it away. We would like, in the ideal state, to just think about our application as input-output. We get some input, we run some business logic on it, and we deliver some output, and that's it. That is really that's the goal here, right? That's the dream that we have. Static site is easy. We know how to do that. We've done that for years. We use S3, we use CloudFront. So let's think about what else AWS has to offer, and sort of traditionally how people have used AWS to host their sites and their web apps. So as mentioned, we can take the static site, put it up on S3, deliver it through CloudFront. Pretty simple, pretty straightforward. If we have backend components, we can set up EC2 instances. This is sort of analogous to using a separate VPS like Linode or DigitalOcean. Now you're just paying for virtualized servers, and you can set those up. More recently, they have introduced Elastic Container Service, which takes that idea, abstracts it slightly so that now we're setting up containers rather than actual virtualized machines. Both of these are self-managed, but have worked out pretty well for a bunch of people. They also have this Heroku-esque product called Elastic Beanstalk, where you choose your runtime, you choose your components, you pay for tier of expected usage. But let's talk about Lambda. Lambda is something pretty cool. I'm sure many of you have heard of it. They introduced it fairly recently. If you haven't, it's essentially on-demand computation. So rather than setting up EC2 instances, managing those kinds of things, it abstracts the execution environment to a runtime. So you choose, I want to use Java, I want to use Python, CPython, I want to use Node.js, and you set up your code and you set up how it gets called, what kind of events it responds to, and you just do that. So it scales to handle each request. If you're if your code, let's just say, is getting hit pretty hard, then it scales up, it adds more to it. If it's not, if it's fairly low volume, it scales down, and that all happens without you actually thinking about it, without you worrying about it. It does that with just your code and just understanding how it maps that to its own execution environment. Additionally, the cost and provisioning happens purely by request. So, again, you're not paying for what they think it's going to cost them to run it. You are paying for what it actually costs to run your app. So you pay by allocation of memory, you pay by CPU utilization over time. So, for instance, pulling these numbers off the AWS website, if you allocate 512 megabytes of memory, have your code get called 3 million times in a month, and each of those requests takes 1 second, you'll pay around $18 for that month, right? So there is some cost to it, but it's fairly low cost, and there's no extra cost for using it over, let's say if you were to perfectly scale your EC2 instances up and down to match, there's no extra cost over that. So that is an interesting methodology, that is an interesting product that we can use, but how do we sort of connect the dots? And that's something that Amazon introduced last year with API Gateway. API Gateway kind of serves as the glue. It allows you to set up a REST API with authentication, routing, resources and things like that, and have that API sit in front of Lambda functions. So we can construct a full web app like this, where we have S3 delivering the static assets of the site, delivering the HTML, the JavaScript, the CSS files. We have the REST API set up through API Gateway that, on demand, upon each request, executes Lambda functions. Those Lambda functions, if we say, okay, let's store our data in DynamoDB, we'll hit DynamoDB on each request. For posts, we'll add to it. For gets, we'll just read from it, scan it, return that back. So what you have then with this infrastructure is a web application, a full web app that does sort of the bare minimum of what you'd expect from a web app. It has a front end, it has a REST API, it has a persistence layer, without actually provisioning any servers, without actually thinking about what is serving my code, how many servers are there, what are the parameters of those servers. And this is a really powerful way of thinking about it. So let's give a practical example and sort of go through what that can look like. Have the code there up on GitHub. You can pull it down. We will also walk through it now, but you can take a look at it later and play around with it. I decided to build the status dashboard in Clojure and ClojureScript. Part of the reason was wanting to experiment with it, but really wanted to show that you can build these applications in languages and platforms that aren't just JavaScript. A lot of people say, I don't really want to use Node.js, I don't really like JavaScript, but there are alternatives, and just saying that I'm going to run on the JVM, I'm going to run on the Node.js runtime, I'm going to run on CPython runtime, those three platforms, runtimes, give you a lot of different options. So we can build a full web app that's not in JavaScript, that has the front end and the back end written in the same language, in this case Clojure, because we have ClojureScript that compiles down to JavaScript. So if you haven't seen Clojure before, if you haven't seen any Lisp syntax, I pulled a Clojure lesson from Uncle Bob Martin, very comprehensive lesson on the syntax. So this is how you'd make a function call in a traditional, let's say, C-like language, f parentheses x. This is how you make the same function call in Clojure. You just move the parentheses, and that's it. Obviously not entirely comprehensive, but this should be enough to get you guys through the actual exercise. So DynamoDB, if you are unfamiliar with it, is a document-oriented database where what we set up is a partition key. This is like a primary key. This is what tells Amazon how they can shard your data across their servers. And then you can additionally set up a sort key or a range key. And so if you set up both, then the combination acts as like a dual primary key. Otherwise, just a partition key acts as your primary key. In this case, really all we want to show are, just at a given point in time, was our web app up and running, and what was the response time, right? Fairly basic dashboard. That's all we really care about. That's all we really want to show. So we, for this table that I have set up, I have set the partition key to be the event ID, which is just a UUID, essentially. Using a UUID is nice because it does give us some time component, at least in the V1 UUID, but is random enough that Amazon can use it to shard our data across. And then we use the timestamp as the sort key, and that lets us order on that and query based on that. API gateway, REST API setup. You can set up resources and endpoints. This is just a setup for our health check method. Just has a GET request, a GET endpoint. And you can set up authentication through IAM users or API keys. And it has cores as well. So it does understand that it is going to be used along with web app front ends. And so you can set up cores. All those things are pretty easy to set up through there. Monitoring and logging is a pretty important thing. You are ceding control of your runtime to Amazon. So how do I know when this code gets called? How do I see events through it? So CloudWatch has logs and metrics available. So you can see information about how many times it was invoked, how long it took, what were the success and error rates of it, and other sorts of things like that. Additionally, anything that you print out, so pretty common first step of logging, right, is just to write the standard out, just print whatever the state of my data is at a given point in time. That gets written to CloudWatch logs as well, so you can actually monitor things through that. Okay, so let's actually dig into this. Just let me see it too. As a little preview, this is what this looks like. There's certain things that will be changing, but fairly basic front end that has the uptime. So in this case, it's just a straight line or dips when it fails, and the response time in milliseconds. Okay, so this is a Clojure project. Lingen is sort of the tooling that we use to build this. So we can have this project file that we set up our dependencies and our build processes and things like that. And we can set up different profiles here. So here we can denote that we have sort of different components of our application and test those, build those independently. So let's go through our health check function, and I'll be walking through this. The main function here is just this sort of server up function. It is a stub. In this case, our server is not very stable. It fails about 5% of the time. If you're running that in production, you probably wouldn't be running it for very long, but it makes for a nice demonstration in this case. So this just returns a Boolean. Is a random number between 0 and 1 greater than or equal to 0.05. 5% of the time it fails, the rest of the time it succeeds. So we want to wrap that function in a bit of JSON and have Amazon execute that and return that. So what you need to declare for Lambda in the Java runtime and for all of them is a handler function to execute. So in this case, we'll use handle, and this is a standard set of parameters. So in this case, we want to set this up as an endpoint, as an API endpoint, right? Where in real life, if you were actually building this, you would probably have, this health check function actually should check your databases and check your cache and, see if everything is actually up and running, and write that back out as JSON. So for the stream handler, which is what Amazon considers to be a Lambda function that runs like an API endpoint in response to streamed events, you have three parameters to accept. You have an input stream, which for Java is just a IO input stream, an output stream, and a context object. And the context object just has information about the actual runtime. So maybe how long it's taken, how much memory is being used, how much memory is allocated, things like that. So things that you might want to know if you have long-running jobs or if you are sort of logging all of these things for calculating and keeping track of your costs. But in this case, all we care about is writing that stream back out. So we don't actually need to worry about the input or the context. All we do is, in our handler function, we open up the output stream, something like a file descriptor, and we construct our JSON string that just has a single key, healthy, and it just checks, it just executes that function and returns true or false. And then we write it to the output stream. So when we upload this jar and we tell Amazon and we tell Lambda to run this function, they will supply those variables for you. In the case of testing locally, we can set up a main function just to have line and grid run it and just test it locally. And we could have just ignored those variables, or you can test it with other things as well. And so we can see that that actually works. We can make this API request. Can you guys see that at the back? I'm not sure if that's large enough. OK, I'll do. OK. So you can see that it gives us back a JSON object. Pretty straightforward there. So once we have that set up, we need to actually test this, pull from this, and populate our table. So we have this status job namespace where it's pretty straightforward. There's just a few steps. We make a GET request to that endpoint. So again, printing to standard out just writes it to the log so we can later go on and see how long each of these took, any additional information like that. It's fairly straightforward. All we do is get the URL, and we tell it to expect JSON. We then need to take this JSON and convert it to a DynamoDB item. So all we do is we instantiate an item. We set the primary key to be this event ID, which, again, as mentioned before, is just a UUID. Set the timestamp, and we just set these fields. Pretty straightforward. The execution time does come from this library. That is something that you could calculate yourself, or in this case, Clojure's HTTP client library has that as a parameter. Then all we do is we just send this to DynamoDB. Fairly straightforward. And again, we can test it locally if we want, or just set up with Amazon. In this case, the event source for this, to this point, we've been talking about these event sources as like API endpoints, right? Using these in a web app. This event source is going to be on a cron, right? We essentially want this to happen in the background. We really want it to happen, every minute or every few seconds even, really would be ideal. But at the current moment, the highest granularity that you can get for Amazon's cron setup is every 5 minutes. You can work around that with SQS and SNS and sort of having that set up to do it more frequently. We won't talk about this now, but if you want to know more, there's a good talk I can send you guys. Just let me know later. So we'll have this job set up to run every 5 minutes. And so this will actually populate our DynamoDB table. So we have that populated. And the last thing we need from a backend perspective is a way to actually get that data back out. So we have this getStatuses namespace that we expect it to sit behind an API endpoint, right? So our front end will pull this endpoint for data. And so we have the input-output context arguments as well. Fairly straightforward. This one as well, all we do is we make a scan to DynamoDB, say timestamp greater than or equal to, in this case, I have just said last 12 hours to simplify it. You can have that accept as a URL parameter or things like that. There are options there. In this case, last 12 hours, and let's write it out. Last thing we have is our front end. The front end is ClojureScript delivered, compiled down to JavaScript using the Regent library. So Regent is a set of ClojureScript bindings over React. So many of you are familiar with React's view model, sort of the declarative DOM and virtual DOM way of building front ends. Not going to get into it too much, but just want to show that we have this set up. We have a component for each of our charts that makes an AJAX request to this endpoint and creates a chart using the Chartist library. Okay, so let's again take a look at it in action. Here is what this looks like. So this looks pretty good. This is pretty basic. But okay, let's say that I actually think these labels are hard to read, right? If I say, in this case, what we're saying is every 10 minutes, if it's on the 10, show that label, so 120, 130. But that's still pretty crowded, so let's actually just change it to do on the hour. So that's pretty straightforward. In fact, I have that written here. All we have to do is just change a few lines here. Comment out a few lines. And so we have our app changed. And this is running locally, but we do have the same thing in production. So let's deploy it just to walk through that and just to show you guys how it can be done. So typically what you would do is you would compile an Uber jar, which essentially compiles down the Java or all the Clojure code into a jar. And we also have a profile here set up to compile the JavaScript as well and make some optimizations. In this case, because it's a little bit slow, I'm just going to skip that and upload the unoptimized code. So we have, again, this whole site that we can just dump into S3. And now if we go back to the site that's in production, we can see that it's changed as well. All right, so you can take a look at the kind of GitHub if you'd like. But let's take a look now let's talk about what we've learned from this. Okay, we've learned that it's possible to write code as code. We wrote some Clojure, wrote some ClojureScript, didn't think about how it was running, and it just ran. The app will scale up and down as needed. So if it gets a lot of traffic, if you have a lot of users hitting this, it will scale up and down. And we can still write in a multitude of platforms, right? We can write in platforms, a bunch of languages to target those. But what issues are there? So you still do have to understand at least some component of the execution environment, right? It does abstract away most of the detail for you. But I want to talk about the execution environment, and specifically, if you look at the response time, right, how there are these spikes here. And in a production app, those spikes might correspond to database traffic or some certain resource being slow. Here, that corresponds to JVM warm-up time, right? This application is running on the JVM, so you have to understand where JVM warm-up time will happen. Amazon does do a pretty good job of caching JVM state so that for subsequent requests, it can use the same state. But it doesn't, it's not mind reading. It doesn't, understand what will happen. And so there is some JVM warm-up time there that you have to deal with. So that just as a way of saying that you do have to understand some components of how this is going to run. Abstraction isn't a silver bullet. If you need control over your application, if you need to understand exactly how it's running, exactly what servers are being used, what servers are being called, if you have highly complex systems, then this kind of setup isn't really going to work, right? It's a good starting point, it's a good place to put some things, but it's not going to work for everything. You have tighter vendor integration, right? You are tying yourself a little more closer to Amazon. If you're just using, for instance, EC2 instances from them and they go away, then you can port those over. In this case, it's a little more effort, right? Because now you have to figure out a new execution environment. And the tooling still does require a little bit of manual work. So you see there, I manually copied my files to S3. You can set up your own wrappers for these kinds of tasks. There are frameworks out there that seek to make this a little easier. So Serverless, which was formerly called JAWS when it came out, is a framework that lets you write, sort of do very similar things in JavaScript and Node.js, and will simplify some of the deployment stages and things like that. But it is still something that you do have to understand. Overall, though, this is a great tool to use. It's a great way of building new things and getting them up and running, and sort of seeing where we want to go in the future of writing code as code and letting the execution environment sit off to the side as like an appendix. All right, thank you guys very much. I will take questions. First, I want to say that MediaMath is sponsoring the reception outside after this. So come grab a drink, come say hi. There are a bunch of us floating around in shirts. If you want to know anything else about how we build our products or kind of things we're using, new things we're trying out, would love to talk to you guys about it. And yeah, thank you guys a lot. And any questions? Yep.
Are there any safeguards for defending against like a DDoS attack given that it's so easily?
So the question was, are there safeguards for preventing DDoSes? And the answer is sort of. You can set those through API gateway. You can set rate limits and things like that. I'm not sure if there are plans for sort of more sophisticated DDoS detection methods, but that is available. Yep.
How do you handle authentication with the API gateway with the serverless architecture?
Good question. The question was, how do you handle authentication? And what you can do is you can store those things in a different Dynamo table and have, similar to that you might do JSON Web Token and have that sort of translate into a user session. You can do a similar thing with it. It does require a little more legwork because API gateway won't understand automatically, that kind of authentication. API gateway does let you do authentication with IAM user, but you could translate that. It does still require a little bit of manual work there, but it's definitely possible using just a separate Dynamo table. Oh, even better. Yep.
Do you have a strategy for dealing with Dynamo's connection limit? Like if there's a bunch of lambdas running and they all want to grab a connection to DynamoDB and there's not enough in the pool, is there a way to throttle that?
That's a good question. So the question was, is there a strategy to handle Dynamo's connection limit? Again, along with rate limiting, the short answer is that it does require some manual work there. It does require sort of understanding what the limits are and using a rate limiting in an API gateway to use that as the throttle.
Is there a concept of like queuing requests? So if you only have n number of lambdas running at one time, but you still keep serving and queuing requests?
I believe it will queue requests in that case. I'm not entirely sure, but I can look into that. All right. Thank you guys a lot. Have a great day.